as you know, my name is Sarah. I am a senior software engineer for Codesmith, and I also am the lead engineering instructor for the New York program. So my role is about 50% engineering, 50% teaching, which is great for me because I kind of get the best of both worlds. Way back in the day, my interest in code was kind of sparked by like the MySpace days where I'd spend a bunch of time playing with my layout and things like that. I started seriously studying coding back in 2019, and that's what led me to Codesmith. I went through their program, and I've been lucky enough to have been working for them ever since. I was an engineering fellow for a little while, and then I became an instructor. I've also done some contract work for other companies. I also want to apologize. I'm in New York City, and they are doing some sort of construction out on the street, so hopefully it's not too loud for you all. But you've heard a little bit about me. I'd love to tell you all a little bit about Codesmith before we get into all of the fun stuff with Clojure in JavaScript. So today we're going to be talking about Clojure. As you know, I work at Codesmith. Tamar here is from Codesmith too. I believe she dropped some links in the chat with some resources that we have available. And if you're wondering what Codesmith is, we have a few flagship programs. So we are a software engineering immersive program really geared towards people who are already maybe at like a junior level in terms of engineering and wanting to level up their skills to be marketable for mid to senior level engineering jobs. So we have two flagship programs, a 12-week full-time software engineering immersive. It is 6 days a week. Very, very intense for 3 months. We have everything's remote right now due to COVID, but we have one on Pacific time, that's our LA campus, one on Eastern time, that's our New York campus, the one that I teach at. And we also have one on Central time that is going to be remote no matter what the COVID situation is. We also have a 38-week part-time immersive program. So this is a really great option for people who can't just quit their job and do nothing but code for 3 months. It's during the evenings on Pacific time, 5 to 8 p.m., Monday through Thursday, and then during the days on Saturday. We also have other resources and learning opportunities. So we have some under the hood courses that are kind of 4-week modules, really designed to dive very deep into one specific area of tech. We currently have one on Node if you're interested on how JavaScript changes when it's working in the Node runtime environment rather than the browser. And we also have one on data structures and algorithms. We also have some prep programs, free workshops, and learning resources, an educational platform called CSX. So lots of things to check out. Codesmith is kind of built on a few of these core philosophies. So our curriculum does go over computer science fundamentals and kind of like things that you would learn if you were studying computer science. But most importantly, you get to put all of that into practical applications. So you learn things like React and Node and Express and SQL. We also have industry leading outcomes. So our average salaries are $120K for our residents that graduate out of New York and $116 for our residents that graduate out of LA. My favorite thing about Codesmith, though, is the alumni network and the supportive community. We have an incredible community of residents, and we also very much try to do our best to close the gender gap in tech. We have a lot of additional resources and support and community events for our women and non-binary residents and alumni, as well as those just in our learning community. So, I think there's a shift in tech happening right now where there's a lot of people who are passionate about tech, but also passionate about people. And so Codesmith is really striving to kind of create that next generation of really empathetic engineers, and most importantly, more diverse engineers, because as we know, diversity of perspective is going to be, I think, what changes the world. We have a quick slide on outcomes. These are a few of our grads. And usually our grads get 86 of them get hired within 180 days from graduating. Like I said, the median salary is 120 in New York, 115 in LA. Pretty impressive numbers in terms of outcomes. So this is all verified data too. You can check it on CER, which is the Council for Integrity of Reporting and something, but they have all of the data as well. It's also audited by somebody else. So I'm really excited to get into you know, the hard parts, Clojure. We're going to go under the hood this afternoon. Thank you to everyone who introduced themselves in the chat, sharing where you're from. I really love that we have people just like from all over the world here. That's really lovely. So we're going to get into Clojure, because Clojure is one of the most esoteric JavaScript concepts. It's one of those things that's used in so many different features of JavaScript without people even realizing it. And I think that it's one of those things that if you really understand what's happening with Clojure under the hood, you're going to have such a strong mental model for how you can use it to your advantage in a bunch of different situations, whether it's a very simple sort of algorithm or something more complex when you're working with like asynchronous code or iterators and generators. Clojure is what allows us to have these pro-level functions like once and memoize. Memoize and once are very common interview questions. They are also just common out in the world, right? We use once if we want a function just only to be ran once, and we need some sort of persistent memory to keep track of that. That's not in an external variable. Memoize allows us to cache certain calculations if they're computationally expensive, so we don't have to keep doing those calculations. A lot of JavaScript design patterns use Clojure. So the module pattern, NPM, if you're familiar with you know, downloading in libraries and packages in Node, all of that structure is built off of Clojure. It also allows us to build iterators and maintain state in an asynchronous world. So, you know, asynchronous JavaScript is kind of how we have the modern internet the way we experience it now, and it wouldn't be possible without Clojure. So, you know, this is kind of what we're diving into today. So before we get into any, you know, the more advanced code, we're going to be talking first about just some principles in JavaScript. You know, this workshop truly is all levels. I don't know what level everyone here is at, whether you already are working as an engineer or you're just learning, but just there are some key things to kind of remember about JavaScript when we're going through these examples, so that we are, you know, able to keep a strong mental model of how JavaScript is operating under the hood. So functions, first and foremost, we know that we have functions whenever we want to bundle up some set of instructions, some piece of code, slap a label on it, and be able to use it later on, right? So we don't have to repeat ourselves when we want to execute the same functionality. So functions are ways that we can define specific instructions and then call, invoke, execute, run it later. JavaScript is a synchronous language, which means it's executed line by line, right? So we're going to be keeping track of the thread of execution while we're diagramming out code, because JavaScript reads code line by line, left to right. And so it's important that we realize sort of where we are, what function execution context we're in, what piece of code is being run as we go through these examples. And last but not least, we need some memory, right? We need some places to actually store any data that we might need to access later. And so when we have memory, we have a global memory that exists within the global execution context of JavaScript. And then we have local memory. Every time we invoke a function, that local execution context also creates a little memory for us to keep track of. So in this example, right, we are declaring a variable num, assigning it the value of 3. We are defining a function multiplied by 2, which takes in one argument input number, and we are declaring a constant result, multiplying the input number by 2 and returning that result. So we are invoking the function, right, by using these parentheses, and we are storing the result of that function to global memory using these labels output and new output. So with that in mind, with those kind of basic foundational principles and pieces in mind, it's important to also know that functions can have multiple names in JavaScript, right? So functions are just a set of instructions, a block of code that we want to save for later. And we can give that set of instructions multiple different labels, because there are two different parts when we're defining a function. There is the function's name, which is the actual label we give it. That's what we define right here after the keyword function. And then there's the definition, and the definition includes the parameter and everything that we've defined as part of the function definition. So behind the scenes in JavaScript, what happens is, since functions are a composite data type in JavaScript, when we give it a label, it's essentially just acts as a pointer to some place in the heap, which is just kind of like the JavaScript memory, right? So I can rename a function if I need to, give it a different label, and it will point to the same function in memory. So let's take a look at that in action. I'm going to be diagramming a lot today throughout the workshop. I can't remember who said it, but you can use the Q&A to ask questions. I'll be taking questions throughout if you have any, and then we also will have some time for questions at the end. But let's diagram out this bit of code to start. So this is kind of like my blank slate. I have a place for global memory. I have a place for the call stack. If you're unfamiliar, the call stack is how JavaScript keeps track of what execution context we're in. And so since we're initially starting to run our code, we are in the global execution context. And the first frame on the call stack is going to be our global execution context. And now we're going to diagram out this code line by line. So what's happening on this first line of code, right, is we are declaring a function multiply by 2. JavaScript tends to hoist function definition. So JavaScript will immediately just save this function definition to memory without actually running any of the code inside of it, right? Because we're just defining the function. We are not executing it yet. So I'm going to add to my global memory the label multiply by 2, and I'm going to assign it a function definition. That little box with an F is going to be my sort of logo for function definition. So we know that in our global memory, we have a label multiply by 2 that points to a function definition. On this next line of code, we're declaring a constant output in global memory. And we are assigning it the value of invoking multiply by 2 with the argument of 9. So since we are invoking a function, we are going to open up a new local execution context, which means a few things happen in JavaScript when we execute a function. We push the function to the call stack so that JavaScript knows what execution context we are currently executing code in. So we are going to push multiply by 2 to the call stack. We are going to open up a local execution context. So this is for multiply by 2 with the argument 9. In our local execution context, we know that in addition to global memory, we also have local memory. So we're going to set up a little local memory in here so we can keep track of any variables defined in the actual function definition. So we have local memory. And now that we have all of this set up, the thread of execution, which we will call toe very affectionately, thread of execution, is going to move in to the multiply by 2 local execution context. Once we're finally here, that's when we can actually run the code in the function definition line by line. So we get to this first line right here, const result, and assigning it the value of input number times 2. So we're declaring a variable result inside of local memory. And we are assigning it the value of input number multiplied by 2, which, since we know our argument is 9, is going to be 18. We then hit this line where we return results. So how JavaScript is going to look for that variable, it's going to check its local memory and say, hey, is there a label in here? Results. There sure is. So it will grab this value of 18 and return it to where the function was executed. So output is where we executed the function. That value gets returned out. And since we are returning out of the function, a few things happen. We pop multiply by 2 off the call stack. We garbage collect this execution context, which is just JavaScript's way of deleting it. And the thread of execution goes back into the global execution context. Oh no. My erasing, oh, there we go. I noticed that it didn't reflect on the screen when I had erased everything. So we then move on to this line of code right here, where we're declaring a constant new label for multiply by 2 and assigning it the value of multiply by 2. So what happens when you actually write this line of code is JavaScript is going to check, hey, do I have anything in my global memory by the name multiply by 2? And sure enough, it's going to look to global memory and it's going to find this function definition right here. So JavaScript just grabs the function definition, and that's what we assign to new label for multiply by 2. So it's the exact same function definition, we've just given it a different label. So this new label for multiply by 2 has no idea that it used to be named multiply by 2. So when we get to this line where we're declaring fresh output, we declare a constant fresh output, and we are invoking a function, which means we need to push, I'm just going to call it new label for sake of space, to the call stack. We are going to open up a new local execution context for multiply by 2. Whew, it's a wordy one, and with an argument of 10. When we get into this execution context, we're declaring a local memory. We are now in the body of the function definition. The thread of execution moves in here. And we're declaring a constant result in local memory. And we're assigning it the value of input number times 2, which is 20, right? We then return that result back out to our global memory. We garbage collect this execution context, and we pop new label off the call stack. We've then reached the end of our code, and that's that. So really, this is just to illustrate that we can give functions different labels, and they still remain the same in terms of function definition. New label for multiply by 2 and multiply by 2 are pointing to the exact same place in memory where that actual function definition is stored. Closure, as we saw, every time we closed out or garbage collected one of those local execution contexts, our entire local memory would be deleted, right? It would be garbage collected. We'd have no memory of what that result variable was in local memory. So when our functions get called, we create this live store of data. That's our functions execute inside of our functions execution context. When the function is finished executing, the local memory is deleted, right? But wouldn't it be handy, wouldn't it be nice if our functions could hold on to that live data in that state in between executions? So this would allow our functions to have an associated cache or persistent memory, which is huge. It's groundbreaking. But it all starts with us returning a function from another function. So in JavaScript, functions can be returned from other functions, right? Because there are two parts to a function. There's the label and there's the definition. And we can return the definition as a value from a function. So let's see what that looks like in action. We are going to diagram this out again. A different bit of code this time though. So we are in our global execution context. We are going to push global to the call stack. And then we're going to start going through our code. So the first line of code, we are declaring a function, create function. I'm going to go ahead and store that in global memory rather. So I have this function definition. The next line of code, I'm declaring a constant generated func. So I find this label generated func, and the value of generated func is going to be the result of executing create function, whatever that returns. So since we are executing a function, a couple of things have to happen. We have to push create function to the call stack. So create function is pushed to the call stack. We have to open up a local execution context. We got to get our local memory set up. Oops. And then the thread of execution is going to move into the local execution context of create function. So once we're here, we see on the first line of this function definition, we are declaring a function multiply by 2, and that's going to be stored in local memory. So we give a label multiply by 2, and we assign it the value of a function definition. The next line of code that we hit is this line right here, where we're returning whatever is stored at the label multiply by 2. Now, how JavaScript finds this is it's always going to check local memory first, right? So it checks first its local memory. It finds that there is a label multiply by 2. And what exists there is this function definition. And that's what we're returning. We're returning only the definition. So let's see if we can just copy this. So now generated func, its value is the function definition that create function returned. Since we returned out of this function, we have to garbage collect our execution context. The thread of execution goes back into the global execution context, and we pop create function off the call stack. This next line of code right here, we declare a constant result. And we assign it the value of invoking generated func with the argument of 3. So since we're invoking a function, we have to push it to the call stack. We have to open up a new local execution context. And we need a local memory. And the thread of execution is going to go into this local execution context. So once we're in here, remember JavaScript has stored the function definition of multiply by 2. Though it doesn't know it's called multiply by 2 anymore, now we know it as generated func. But we're going to match up our parameters with our arguments. So the parameter is num, and we have passed in 3, right? So num is going to have the value of 3. And then we actually execute the code, which is just returning num times 2. So we are going to return 6 to our label results. Then since we're returning out of the function, we garbage collect. The thread of execution goes back into global, and we pop generated func off the call stack. Since we've reached the end of our code, that's all there is there, right? So this is the very beginning of how we can execute Clojure, by realizing that we can return a function definition from a function in JavaScript. This is something that you can't do in some other languages. This is one of those things that's like not necessarily unique to JavaScript, but almost. We can also call a function in the same function call it was defined in. So understanding these intricacies of how scope is working in JavaScript, where JavaScript is checking for certain labels and pieces of data, is really important to realizing why it is Clojure works and how it is Clojure works. So we're going to diagram this out, right? Because as you can see on this slide, when you where you define your function determines what variables your function has access to when you actually invoke or call that function. So first and foremost, right, we are in the global execution context. So we'll put that label up there. We will push global to the call stack. And then the first thing that's happening is we are defining a function outer in global memory. So outer is a function definition. Then the next line of code, we are just invoking outer. So since we're invoking a function, we need a new local execution context. We need to push outer to the call stack. We need local memory. And then we can actually, we also need the thread of execution. And then we can actually execute this function line by line, right? So we are going to first start off by declaring a variable counter and assigning it the value 0. Then we're declaring a function called increment counter, and we're storing that in local memory as well. I'm like, can I fit increment counter? It's all these long function names. All right. So then we have a function definition, increment counter. This next line of code right here, we are invoking increment counter, which means we need another execution context, and we need another stack on the call frame, or another frame on the call stack. So we are going to push increment counter to the call stack. We are going to open up another execution context, this one for increment counter. And then we need a local memory inside of increment counter. The thread of execution is going to move into this execution context. So we see that the body of increment counter, the function definition, is just incrementing counter by 1, right? Counter plus plus. However, we know that JavaScript normally it's going to look in its own localized variable environment, right? So it checks increment counter's local memory. Does it find a variable counter? No, it doesn't. And so it checks outer's local memory, because this is where this function was defined, right? We defined this function inside of the context of outer. And since we defined the function in outer, we have access to these variables, right? So it finds the variable counter in outer's local memory. And it goes, great, okay, I guess I'll increment that by 1. So, oops. So we increment counter by 1. Counter is now 1. Right? That's the last line of code inside of increment counter. So we garbage collect increment counter's execution context. The thread of execution goes back into outer. Increment counter gets popped off the call stack. And then we realize, okay, this is actually the last line of code inside outer too, which means that we also need to pop outer off the call stack and garbage collect outer as well. So this is a little hint as to how Clojure is working, right? Instead of it looking only in its own local environment and the global environment, it also looked to where it was defined and what variables were there. So let's see that in action. I see that there's a question in the Q&A. Don't we need to invoke increment counter func? Here we called outer func. Yeah, Priya, so we actually invoked increment counter inside of this function outer. So we defined it inside outer, and then we invoked it right after we defined it inside outer. Okay, I'm gonna keep on moving. So we can also call a function outside of the function call in which it was defined. And remember, where you define your function, it impacts what variables you have access to. So Let's see it in action. Okay, we have, gotta get our global execution context set up. We're gonna push global to the call stack. And then we are going to define our function outer, right? That's the first line of code, is we are defining this function outer. Then we have this constant myNew function, which its evaluated result, or its value is the evaluated result of invoking outer. So we'll store myNew function in global memory, right? And in order to figure out what the value of myNew function is going to be, we have to invoke outer. So we are going to create a new execution context for outer. We are going to push outer to the call stack. The thread of execution is going to move into outer. And we are going to set up our local memory. So once we have set all of that up, we actually get into the body of the function definition. The first line of code, we are declaring a variable counter and assigning it the value of 0, right? So we're storing that in local memory. Then we're declaring a function increment counter, our old friend from the last example, and we are storing that in local memory. Then the next line of code is this one right here, where we're returning whatever we're storing at the label increment counter back into the global execution context. So if we look to our local memory, we see that we are returning this function definition. So we're going to return that out to the global execution context at our label myNew function. Now, this is where Clojure comes into play, and this is where it gets fun. So we have executed, or we have finished executing the code of outer, right? So we garbage collect this execution context. The thread of execution goes back into global, and we pop outer off the call stack. Now, remember, when we garbage collect an execution context, that means that its local memory is gone. So our next line of code is right here, where we invoke myNew function. And so since we're invoking a function, we need to push myNew function to the call stack. We are going to open up a local execution context. So myNew function. We are going to set up our local memory. And then the thread of execution is going to go into myNew function. So once we're in here, remember that this is the function definition of myNew function, right? It used to be known as increment counter within the context of outer. Now it's known as myNew function. And this is the only line of code in that function definition. So knowing what we know about JavaScript, logically, it will check first its local memory for the variable counter. We don't have anything in local memory for the context of myNew function. So if we were following JavaScript's just standard rules, the next place it would look would be global memory, right? And as you can see, we don't have a variable counter in global memory. And this is where Clojure comes into play. So when we returned this function definition of increment counter from outer, we returned the function definition, but it also brought along some other things with it. And for simplicity's sake right now, I'm going to call it a backpack. So myNew function, when that function definition of increment counter was returned, it brought along this backpack of some other stuff with it. So in addition That's my terrible drawing of a backpack. Let's give it a fun color to make it look a little bit better. So in addition to the function definition, it also brought along this backpack of some things it thought it might need. Remember, this is all about functions having access to the variables that were present where they were defined. So if we think back to when we first defined increment counter, we had a variable counter within the context of outer. And so increment counter brought that variable counter along in its backpack. So inside of this backpack, we currently have counter with the value of 0. So when we're inside this execution context of my new function, it first is going to check its local memory. We don't have a variable counter. Before it checks global, it is going to look inside its own backpack, that data that it brought along with it. And so it finds it in here, right? Because it was present in the context in which increment counter, now known as my new function, was defined. And so we are going to increment counter to 1. That's the last line of code, right? So we are going to garbage collect this execution context and pop my new function off the call stack. The next line of code is another invocation of my new function. And so we are going to open up another local execution context. We're going to push my new function to the call stack. Thread of execution is going to move into my new function. And then we also are going to set up a local memory, right? Remember that this is the function definition that we are executing, right? Counter plus plus. It is going to look first in its own local memory. It doesn't find it. So then it is going to pivot and look in its backpack. And we know that we have a variable in there called counter, and it starts off as the value of 1. We are then going to increment it to 2. It's the end of our code. We are going to garbage collect this execution context and pop this off the call stack. This is how Clojure works. This is what makes Clojure such a cool concept. It's like my favorite thing in JavaScript, right? It gives us persistent data across multiple execution contexts without having to use a global variable. So this counter variable, it's only accessible inside this backpack. I don't have to worry about somebody else defining something called counter in the global context and overwriting it or messing with it. It's only accessible within the context of executing my new function. So the backpack, right, when increment counter is defined inside outer, it gets that bond, that link to the local memory inside of outer. When we return increment counter's code, we give it a new name, my new function. But we maintained that bond to the environment in outer. So it gets returned out attached on the back of increment counter's function definition. That's why I like the term backpack. When I was kind of like diving into Clojure under the hood in my own learning journey, it was really helpful for me to imagine like literally the function definition bringing like a backpack along with it with all the variables it might need. And so this is that bond that it maintains even after the execution context is garbage collected. So when we run my new function in the global execution context, it's going to first look in its own local memory, but then it looks in its backpack to see if it has anything in there. So what can we call this backpack? We can call it a lot of different things. So closed over variable environment is a name that you could use for it. That's kind of where Clojure comes from, because it is a variable environment, but it's closed over, right? It's not easily accessible. It's only accessible in relation to that function definition. My personal favorite besides backpack, because that's so fun, is persistent lexical scope referenced data. It is a mouthful, but like if you're in a job interview and they ask you about closure and you start talking about it and you're like, yeah, you know what I think a more precise name is for this? Persistent lexical scope reference data. They're gonna hire you on the spot. Backpack, like I said, that's like a fun terminology. It was really helpful for me to get that visual. And closure is what we mostly know it as. So the backpack or closure of live data is attached to increment counter, then to my new function through a hidden property known as scope, double bracket scope. And this persists when the inner function is returned out. So I want to be super clear. You can't do things like my new function dot double bracket scope, right? You can't access it in this way. I think there might be a way in Chrome to see like what is hiding in that backpack and that closure, but typically you can't see what's in there. So you can't access it this way. If you tried to console log double bracket scope, you wouldn't get anything. But this is a hidden property where this variable environment is living, and this persists when the inner function is returned out. So this is how we get access to this persistent variable store, is by returning a function from another function. You can have more than one backpack. So I'm going to copy this really quickly because I know we are getting close on time, and go back to our diagram here. And let's just see what like a separate backpack would look like in action. So we have this example code. The beginning part is exactly the same as what we just looked at, right? We created a my new function and assigned it the evaluated result of invoking outer. And then that's how we incremented our counter in our backpack for my new function. And now counter is equal to 2. We're going to declare another constant, another func. That's what I'm going to call it. It also is going to be a function definition, right? Because we are going to invoke outer. We are going to open up a local execution context for outer. We are going to open up a local memory. And then we are going to declare a variable counter and assign it the value of 0. We are going to declare it a variable increment counter as a function definition. And then we are returning this function definition when we return out of outer. So we garbage collect this execution context, but we know now that when we return that function definition out, it's bringing along a backpack, right? It's bringing along the variables that were present when it was defined. So it's the same. It's the same, let's see. Copy, it's the same function definition of counter plus plus. We don't need that circle there. But it brought along another backpack too. And so this backpack, right, we'll give it a different color. And inside this backpack, we have counter with the value 0 because we invoked outer again, right? So this is a separate backpack. This is a separate closure than our first invocation of outer. And so you can have multiple persistent memories for the same context, for the same function definition, because every time you invoke outer, it's creating a new place in memory for that function increment counter, right? So it's like a new version of it, essentially. It's not pointing to the exact same function definition. So when we invoke another func or another function, right, we need to push it to the call stack. We set up our local memory. And it looks first in its local memory for counter. Does it find it? No, it doesn't. So it looks in the backpack. It's going to increment counter to 1. Then we garbage collect this, pop another function off the call stack, and it does it one more time. We open up a new execution context for another func. We push another func to the call stack. We set up our local memory. And it looks in its local memory for counter, doesn't find it. It looks in its backpack, sure enough, it does find it. Counter is now 2. And we have reached the end of our code. So you can have separate backpacks, individual backpacks for the same function. You can have multiple different persistent memories. This is how we have persistent data across function calls. So Clojure is an extremely powerful tool. We can have individual backpacks, right? If we run outer again, and we store the returned increment counter function definition in another function, we just saw that it would be a completely separate backpack than that first one. Clojure gives our functions persistent memories. This is huge. This gives us a whole new toolkit for how we can write quality code, right? This gives us a way to avoid global variables. It gives us the ability to create helper functions like once, right? Because you can store something in the backpack that keeps track of whether or not that function was invoked or not. It allows us functions like memoize, because you can have a persistent cache with a function definition that's only accessible through that function. It allows us to create iterators and generators, which are just ways for JavaScript to iterate through arrays and data sets in a different way than the standard like for loop, but it's possible because of Clojure. The module pattern, NPM modules, importing and exporting when you're building out a repository, that's built on Clojure. And perhaps, I think most importantly, asynchronous JavaScript is built on Clojure. So anytime you schedule a callback or use a promise, right, it has access to the variables that were present when you defined that callback function. And that's why you can mutate some data once you get a response from a network, or once your set timeout is through, or whatever it may be, because it brought along all that data that you needed from it. So Clojure makes a lot of things incredibly possible for us in JavaScript. I know we're like almost out of time, but if anybody has any questions about what we covered today, I'm happy to answer. I'm looking at the chat
to catch you up on that. Everyone is enjoying this visual sort of explanation. I think it's yeah, really good one.
Yeah, we all love Backpack. Backpack like changed the game for me. I feel like I really couldn't visualize Clojure before I like learned the term Backpack. All right, y'all. Well, if you have any questions, you can put it in the Q&A. I have a few like kind of closing up slides. Yeah, the execution context is also really interesting. If you're like, man, I'm ready to just like dive into some things, we do have a couple of under the hood courses coming up at Codesmith: data structures and algorithms and Node. Data structures and algorithms starts November 15th. Node starts November 29th. Feel free to check that out on our website. This is like a 4-week deep dive into these concepts. We also have something called CSX. If you've been working on Clojure, we have a whole section of CSX. It's a free online learning platform. We have a whole section on Clojure. So there's like a lot of like Clojure challenges and algorithms to help you strengthen those skills. We also have some courses, JavaScript for Beginners, CS Prep, and we have free weekly workshops. I teach a lot of them, so I hope you come. We also have women's workshops on Wednesday night, so highly recommend coming to those. We specifically tried to make tech more accessible for women. I think it's so important. It's something I'm very passionate about. So we do have scholarships for people who are female identifying. We have women only free workshops. We have mentorship programs if you're in the admissions or applications process. We also have a special scholarship for our Women Who Code community. So I believe, Tamar, did you share this link for the Women Who Code specific scholarship in the chat?
Yes, I did. I think it's one of the
Okay,
first
great.
ones.
Amazing. So we do have a specific scholarship for Women Who Code if that's something that you're interested in pursuing. And feel free to email me. My email is on here. My LinkedIn is on here. I love to talk about code. I especially love to support women in their coding journey. So please don't hesitate to reach out if you want to connect. Also, if you go to codesmith.io, it has info about all of our programs and also our free workshops. I'd love to see you again. I'm going to check the chat just to make sure. Katie, thank you so much. Any final questions before we wrap up? I think we're going to end right on time. I don't know how we spot that. I have a tendency to go over, so I'm just happy we wrapped it up on time.
It's great, Sara. Like, yeah, everyone has been leaving feedback. It was great. I think, yeah, this was a great way to learn these sort of technical topics. And yeah, like Bharti already asked, another workshop on execution context. So yeah, let us know if, yeah, you would be happy to do that.
Okay. Sounds good, Princia. Thank you. Thank you to everyone who came. It was so lovely to have you here. I hope everybody has a great rest of your Tuesday, and I hope to see you in another workshop sometime.
Great, awesome. Just a quick reminder, or yeah. So once you log out to the attendees, you will get a survey. Yeah, we are trying out new Zoom features, so it should just take like a minute or less. So yeah, let us know the feedback about this. We would really appreciate if you could answer the short 1-minute survey.
Awesome. Thank you so much, Princia. Thank you to everyone who came. Thank you, Women Who Code. Hope to see you again soon.
Yes, thank you all. And thank you, Sara. Thank you, Tamar. And thank you, Codesmith.
Bye, everyone.
See you. Have a great rest of the day.